Okay.
Oh, finally we're live! Hello! And I'm going to kick off the podcast recording.
Oh, okay, we gotta start the recording.
Okay, so we're good.
1, 2, 3.
Listening to Thinkative, the podcast for philosophers, seekers, and the generally curious. I'm Tim Newton.
I'm Matt Parker.
Over there is Jason Reed. Hello!
We've got Gav on camera as usual.
And today we are very, very privileged to have the author of The Logic of Mathematical Discovery.
Not the author.
Yeah, the editor. Yes.
Professor John Worrall.
Yeah.
The London School of Economics.
Yeah, Professor. You know, I know there's a lot of you been waiting around wondering where the broadcast was. Well, it's here now. And of course, we've been
so many angry emails and messages.
It's all due to Tim. Cambridge. Right now,
thank you.
This is a beautiful vintage claret from 2015, brought along by Mr. Worrall. Professor Worrall, who I shall pour you first, sir.
Thank you very much.
Guest of honour. Guest of honour.
Thank you.
Jace.
Thank you.
There for you.
Lovely.
I know you're not driving tonight, so.
No, so I can have a drink.
Of course, Matt.
Nice.
Yeah.
I'm not driving. This is my house.
It is. You haven't got far to go at the end of tonight. Just as
But
well.
I do have to be careful because sometimes I don't make it up the stairs.
Oh, don't you? That's all I've heard.
I kid. Cheers, everyone.
Cheers. Good health.
Cheers.
Lovely to have you on the show.
No, thank you for inviting me.
Wow.
Cheers.
Cheers.
And I, for one,
Cookie
can't
quick.
wait to hear more about all of this, which I am, wholeheartedly ignorant of, I have to say.
That's really nice.
Good.
Maybe it's the anticipation, but
That is going to go down.
Very good indeed, very good.
Delicious.
From what
That is lovely.
Well, let me just start out a little bit here because John and I go way back. We used to be in a band together at the LSE, and I'm a huge fan of this book by Imre Lakatos, Proofs and Refutations, and I think that had a lot to do with me ending up teaching at the LSE. Because I mentioned in my cover letter. And I think that may have helped me to get in good with John here.
Yeah.
And John's co-editor with Zahar. And you were a student of Lakatos's, right? You worked closely with him in the 60s, 70s?
All of those, yeah. Well, he was actually my undergraduate tutor, believe it or not. I mean, it's just amazing to think now that it should have been. But yeah, so right from the age of 19, he was a figure in my life. And then I did a PhD with him and became his research assistant and became a colleague. And then sadly he died very early.
Oh.
And that was in...
And then we did all the work on the book and everything.
What year did he die?
74,
Okay.
he said tentatively.
Yeah.
One of those years anyway, yeah. I think it was 74, he was 52, born in 1922.
Right.
And you wrapped up the book for 1976, right?
Yeah.
But it was originally published in BJPS?
Journal for Philosophy of Science in 4 parts, yeah.
Right.
Well,
That was like
not all of it,
1963,
because there were some
right?
other bits. Sorry?
That was around 1963, or...
Before
okay.
I would say between 63 and 65, it was a sequence of...
A sequence of papers, yeah.
So why, for those of us who don't know, why is it such an influential book, and what does it talk about?
Well, so Lakatos presents a different picture of mathematics from what we're used to getting in school, a very different picture.
Right.
And in the first place, he emphasizes that mathematics is very fallible, that proofs don't always prove, that they serve a different function, such as to sort of decompose a conjecture into sort of smaller parts. So it gives us a different way of understanding. I know, what would you say Proofs and Refutations is about?
Well, that was more or less it. I think Imre genuinely believed that it was a fallibilist theory of mathematics. I mean, we can discuss whether that's true or not. I think what it certainly shows is that the process of arriving at proofs is a very fallible process, and much more, it's not just that people in mathematics start out with certain axioms and then deduce consequences. It's very much tied in with empirical matters, because the whole focus of attention in the book is on a theorem, Euler's theorem about polyhedra, which obviously are physically manifested entities, at least. I mean, they're idealised in mathematics. But, I think whether, as I say, it's the mathematics you finish up with is fallible, as he I think believed, and that's why he was so popular with Popper, who thought that he was extending his fallibilist theory of science into mathematics, which is sort of an unlikely area, or whether it's just a sort of heuristic thing or a discovery thing, not really a claim about the status of the finished product. That's something that people have discussed thereafter, long and hard.
Right, well, let's go back to Popper, because we actually did an episode about Popper. It was sort of a funny one.
Many bottles ago, yeah.
But we did an episode about Popper, but if you can just sort of remind us what Karl Popper was all about and what Lakatos took from him.
Well, in a word, or in a phrase, Popper's view was that all knowledge was to do with conjectures and refutations. He very much disputed what he saw as the inductivist view that in science you go around collecting lots and lots of data, and then eventually some generalisation hits you. He thought that, surely correctly, I think, at root, that scientists are much more exciting than that. You're having ideas the whole time, you're testing those ideas. And that the only thing you can ever really say, and that now we get into the bit that's been disputed, is that a theory so far hasn't been refuted. So he was very much impressed by scientific change, by the change, for example, from classical physics, classical Newtonian physics to Einsteinian physics. Very much stressed the dynamic nature of scientific belief, if you like, although he said he didn't believe, he enforced that he didn't believe in belief, but accepted theories in science were constantly changing, and changing quite radically.
Right, so for Popper, when we go out and we see that the predictions of a scientific theory turn out to be true, that doesn't give us reason to believe the theory. No. It just means we've failed to refute it.
So far, that's the pure Popper line.
Which is a very funny thing, and you had this very interesting dialogue that you wrote. I think there's three gentlemen on a roof or something like that.
On the top of the Eiffel Tower, yeah.
On the Eiffel Tower, okay, right. And what was the point of that?
Well, the point is that you do need to in the end, you have to have some sort of inductive assumption that links the past performance of theories to the future. That Popper thought he solved the problem of induction by showing that there was no such thing as induction in science. That is, no such thing as inferring that the way things have been is a representative sample of the way things will be. Right. And Popper insisted, as you say, the pure Popper line was that all that we can ever say about the theory is that it hasn't so far been refuted. We can't say that it's true, close to the truth, likely to carry on being performing better.
But then if that's the case, you have no reason not to jump off the Eiffel Tower.
Exactly, because Galileo's laws only held so far. You've got no reason to think that it's going to happen. It's going to still be in operation today. Right. Today, when you
so the idea was that you're at the top of the Eiffel Tower and you go, if I jump, I will probably hit the bottom.
Not even that. Popper wouldn't even accept that.
Probably.
Really?
No.
Not even probably. The likelihood everybody else who's jumped.
Of course, he would have accepted it, really. But it's what his official doctrine entitled him to. And he should have said that you can't make that inference, that it's perfectly reasonable to assume that Galileo's law that what freely falling bodies constantly accelerate has only been true so far, and that doesn't mean that it's going to be true in the next 2 seconds. So if somebody claims that they're going to float gently down from the top of the Eiffel Tower, that's up to them.
Yeah.
Whereas I think the rest of us would all say, no, this guy's crazy, we've got to restrain him for his own good.
Yeah.
And Imre, I mean, to be fair, Imre was against that aspect of Popper. So it's really the fallibilism that I think influenced him, whether correctly or not is another matter. But he had this view that Popper was absolutely right, that science is and always will be fallible, which to some degree obviously it is, and he thought that could be extended into the realm of
Now, what does
mathematical knowledge.
sorry.
Yeah, please.
What does fallibilism mean here?
Just that you've got that any theory, no matter how well empirically supported, may nonetheless turn out to be false, and that we should constantly remember, that people thought in the 18th and 19th century that Newton had discovered the truth about the universe, and that was it. That was the end of physics. Basically, it was all done apart from crossing a few T's and dotting a few I's.
Yeah.
Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light, and that was it. And so Popper, fantastically inspired, centrally inspired by the Einsteinian and quantum revolutions, as they're called, where for centuries, decades and decades anyway, Newton's theory had been regarded as the absolute truth, and then it turns out to be completely wrong in all sorts of ways, judged from the vantage point of the later theory. So Newton has then there is a sort of inductive step in Popper, so maybe the same thing's going to happen. Maybe not definitely, but maybe the same thing's going to happen with Einstein's theory, and that's the open-endedness of science, the fallibility of science at the top level.
Which is healthy, to have that fallibility, because it is so easy, especially in this very scientific age. And I know I've seen myself do it over time. Is get ever more empiricist about everything, but not only empiricist needing to see the proof, but also having a real set of assumptions that you believe are totally rock solid, and there is no doubt about it. You just get very sure of your ideas, which is dangerous, because you end up blocking yourself and creating, as we've said before, these reality tunnels, as Robert Anton Wilson said, where you're looking at everything through a very sort of binocular, with very blinkered vision, and it's a healthy. I think it's a healthy energy to have, especially and then to introduce it into science, because science is obviously can be very. I mean, there's a lot of pseudoscience, and there's a lot of stuff which is cock and bull, or we believe cock and bull, but you say. But to have an open mind, to keep the mind open, so long as your brains don't fall out, is a good thing.
That's the issue, though. I think what a sensible person would do is distinguish between fundamental science, frontier science, which undoubtedly is fallible, and it was clearly a retrospective mistake for all those people to think that Newton had unambiguously and definitively discovered the truth about the universe. But underneath that, there are these observational generalizations, like freely falling bodies fall with roughly constant acceleration. Of course, it's not literally correct even on Newton's theory.
Right.
So we modified Galileo's law. We didn't change it completely. We didn't chuck it out completely. It's almost everybody almost falls with constant acceleration, and the rate at which it falls is independent of its mass, which is still absolutely correct. So underneath, TV sets keep on working. Experiments that we know how to do keep on having the same results. So there's some things that are constant in science, but not at the fundamental level. Popper somehow transported the fallibility, or tended to transport the fallibility that undoubtedly applies at the highest level in science to everything, which leads to.
So for Lakatos then, it would be fair to say that fallibilism for him means that even if we have a seemingly very convincing proof of a theorem, it might actually just be wrong. We may have missed something. Is that where the fallibilism comes in for mathematics? And there's my favorite line in the whole book, and this connects with what you were saying, is just this line somewhere in the middle where one of the characters is referring to another, and he says, his certainty, far from being a sign of success, is only a symptom of lack of imagination. And that's how I feel about certainty. I always take it to be a vice. You shouldn't feel certain of anything, right? There always should be room for small
certainty is a vice. Yeah.
Aren't you certain that either today's Thursday or it's not?
Well,
logical truths. I mean,
I might have, you know, of course I could go Descartes on you and say, you know, I may have been misled about the fundamental truths.
But
of
you
logic.
don't believe it. I mean,
I don't believe it, but I leave a little room for that.
Really, even
Yeah.
on logical truths.
Yeah, even on logical
truths.
truths.
Well, I
Well, it
admire
depends. In a way, you're kind of
your
as certain as you need to be.
What's that?
Yeah, well, that's the right
Yeah.
thing. I'm as certain as anything. I mean, I'm a fallibilist about most things, but not logical truths. You know.
Well, so haven't you ever made a logical error?
That's different. Well, that's the whole thing here. I mean, you know, that's the whole. I mean, is he? I think obviously you can make logical errors. I don't make too many now, actually, but my students certainly make a lot. But that doesn't mean that that logic is fallible. I think, and that's the issue really with Lakatos. I mean, you know, obviously people do make mistakes in arriving at mathematical theorems, and they're fascinating. And he was right to emphasise them, and it produces, as we've agreed, a fascinating book. But it doesn't follow from that. It needs more arguing that the end product of mathematics is once the whole process of proof analysis and so on that he described and he's gone through aren't in fact logical truths of a conditional kind, but I think, you know, I think basically it supports it.
I mean, I think it's also worth pointing out that there are people who, for some convincing philosophical reasons, bivalence deny the law of excluded null. And I'm not certain that they're wrong.
Well, I'm certain that they're wrong. They don't. They mean something different. I mean, so for example, intuitionists in mathematics, they don't really, in my book, deny the law of excluded middle. What they say is that it's not true that for every mathematical statement it's either been proved or it hasn't been proved. So they're talking about not about truth. I think every statement, for every well-formed statement, P is either true or false. It seems to me. But what they're denying, which is correct to deny, is that for every mathematical statement, either we prove that P is the case or we prove that not P is the case.
So it's a method of binary. Is it a very sort of binary method of analysis then?
I would adopt a binary. When it comes to logic, you know, obviously I'm much more hidebound and boring than Matt here with his very highfalutin fallibilism. Yeah, I can't convince myself that there's any serious sense in which either. In fact, Lakatos himself, he used to say, because Popper's professorship was in logic and scientific method, and this meant that he lectured at the LSE 1 year in logic and 1 year in scientific method. And 1 year, Lakatos took over doing the logic, and he said, "Look, I know that this guy Popper told you that everything's fallible, including logic, but this stuff I'm going to teach you is completely infallible."
So you heard it straight from the horse's mouth that Lakatos really believes in the infallibility of logic.
That's why the footnotes in here are much more sensible.
That footnote always bothered me.
I can see with your view you would be, but the truth is in the footnotes.
I mean, also
the editorial footnotes written by me.
Right. So John and Zahar wrote the footnote, so they think that that's the best part. I wish I could. Do you know happen to know where that footnote is? I wish I could read it so people know what we're talking about. But basically, there's some footnote in here that says actually Lakatos really believed in the infallibility.
When he says he has somebody joke about today absolute certainty has been achieved, and there's a footnote. I don't know. It's a long time since I rationally reconstructed Lakatos.
Well, I'll tell you what, there's something that I've been wanting to do for a long time, which is to have an actual sort of group reading of a section of Lakatos's book. And
because it's important to emphasize it's a Platonic dialogue in the original Plato sense.
So
you don't even know who's got the truth. That's one of the fascinating things about it. Not even the teacher is always correct in this.
Gavin, I've got to get you to read some of these parts too, okay?
Oh, okay.
Did I not fill up enough? Did you bring one, John?
I did, but it's in my bag, which is downstairs. But we can share, probably.
Oh yeah, maybe you and Jace can share, or Gavin and Jace can share.
I'll sit next to Jace.
All right. So I'll read from the beginning. Okay.
So just to put this in a bit of context, then, what's happening here?
Well,
I need a motivation for my character.
Oh,
there's,
okay.
there's context, right? I'm going to
I'll
start
have
with the
Tweak
context.
the
Okay?
spine around a little bit to get me
Okay, so section 1,
Okay.
problem and a conjecture.
Well,
The dialogue takes place in an imaginary classroom.
Okay.
The class gets interested in a problem. Is there a relation between the number of vertices, V, the number of edges, E, and the number of faces, F, of polyhedra, particularly of regular polyhedra? So, just so for our audience,
yes, please.
let me just do a quick diagram.
Let's have a little look. There we go.
So,
a board. Is that
Imagine materials.
Spain.
Okay, so a polyhedron is
Entering new territory. There we go. This is
Quality.
polyhedron is basically a three-dimensional geometric shape.
Sure.
Okay.
Like
What exactly a polyhedron is
the classic case. Yeah.
is a point of contention throughout the book, right? What exactly a polyhedron is. But
Okay.
here's a
Roughly,
cube, right? So there's one.
6
Now,
sides.
A cube has vertices, which are the places where the sharp edges meet, the
Okay.
corners, if you will.
Yeah.
And it has edges. Oh, that chop doesn't work very well. Is in between the edges, and those are called the faces.
Yeah.
All right.
And so the Euler theorem or conjecture is that the number of faces,
Yeah.
right, minus the number of edges,
Okay.
plus, sorry, I got that wrong. It's the number of vertices
All right.
minus the number of edges,
I want vertices at corners, are they?
Corners.
Yeah, corners.
Where they meet.
plus the number of faces
Yeah.
is always equal to 2.
What?
Yeah. So for our cube, how many vertices do we have?
8.
Okay. And how many edges do we have?
4 and 12.
12, yeah.
Good, very good.
12.
Yeah.
And I'm trying to make this dark so the camera can see it.
Yeah.
And then how many
Okay.
faces do we have?
6.
Yeah. Okay. That's one example where it turns out to be true. Okay, so this is the conjecture. Now,
Yeah.
after much trial and error, the class notices that for all regular polyhedra, V minus E plus F equals 2. Somebody guesses that this may apply for any polyhedron whatsoever. So, for example, let me see if I can draw a tetrahedron.
That's pretty good.
And my two edges are, so a tetrahedron is like 4 triangles
Okay.
together. Shape, right? So you can see 3 sides, and then the bottom is the 4th side.
Yeah.
So once again, that also satisfies the conjecture.
Okay.
And then we can draw 12-sided polyhedra and so on.
Okay.
All right. Now, the question is this true for all polyhedra or not? Right? Okay. So the results corroborate the conjecture and suggest that it could be proved. So now we come to the problem of trying to prove this conjecture, and now our teacher begins.
Okay.
I hope you're suitably deferential to the teacher.
So
okay.
this is part 2
Actually,
of proof.
Unsuitably deferential. The whole point of Lakatos is that you shouldn't be deferential,
Yeah,
to anybody,
okay.
including the teacher. Anyway, I'm playing the teacher in this.
Yeah.
In our last lesson, we arrived at a conjecture concerning polyhedra, namely that for all polyhedra, V minus E plus F equals 2, where V is the number of vertices, E the number of edges, and F the number of faces. We tested it by various methods, but we haven't yet proved it. Has anybody found a proof?
Well, I for one have to admit that as yet I've not been able to devise a strict proof of this theorem. As however, the truth of it has been established in so many cases there can be no doubt that it holds good for any solid. Thus, the proposition seems to be satisfactorily demonstrated. But if you have proof, please do present it.
Now, let me just interject here that much of what the students say in this dialogue are things that were actually said by mathematicians in the history of this problem.
Right.
Now the teacher again.
Okay.
Yeah. In fact, I have one. It consists of the following thought experiment. Step 1. Let us imagine the polyhedron to be hollow with a surface made of thin rubber. If we cut out one of the faces, we can stretch the remaining surface flat on the blackboard without tearing it.
You continue reading and all
The faces and edges will be deformed, the edges may become curved, but V and E will not alter, so that if and only if V minus E plus F equals 2 for the original polyhedron, V minus E plus F equals 1 for this flat network. Remember that we removed one face. Figure 1, which
this is figure 1,
shows that the flat network for the case of a cube.
So this is a cube that we've taken off the. Okay.
So you think of it as rubber.
Okay.
Made of rubber, and that's
Sure.
what it would look like.
Sure.
Step 2. Now we triangulate our map. It does indeed look like a geographical map. We draw possibly curvilinear diagonals in those possibly curvilinear polygons, which are not already possibly curvilinear triangles. This diagonal we increase both E and F by 1, so that the total V minus E plus F will not be altered. Figure 2. Are we going to get figure 2?
That's essentially figure 2 right there. I may have drawn it a bit differently, which is a problem because when we start, yeah, but that's fine. That's figure 2.
So what?
So what we've done is we've taken each of the sort of polygons made up by the faces and cut them with further lines so that we only have triangles.
Yeah,
Okay.
Right? So this is a triangle, this is a triangle, this is a triangle, this is a triangle. There's
Yeah,
nothing
but
there
they're
but
flat.
triangles. They're flat, yeah.
Well,
Okay.
Yeah.
The important thing is that they're triangles.
Okay. Right. Yeah.
Okay.
Right.
And now it's pupil delta who speaks, or are we
No,
there
there's
yet?
a lot more to go.
Oh, carry on,
Let's
teacher.
go.
Carry
Teacher
on.
hasn't finished.
Do you want to jump on Teams? You're better.
Oh,
So
okay.
you can read that and
So
shoot
now
Teams
on
back
step
and I'll
3,
shoot
right,
this
from the triangulated network we now remove the triangles one by one. To remove a triangle we either remove an edge
Like this.
upon which
Don't block it.
Oh, well, yeah.
upon which one face and one edge disappear, or we remove two edges and a vertex upon which one face, two edges and one vertex disappear.
So that would be this case. We remove two edges and their common vertex. Okay, carry on, teacher.
Okay, thus, if V minus E plus F equals 1 before a triangle is removed, it remains so after the triangle is removed. At the end of the procedure we get a single triangle, and for this V minus E plus F equals 1 holds true. Thus we proved our conjecture.
That's the proof.
You should now call it a theorem. There is nothing conjecture about it anymore.
Gavin.
Pupil alpha says.
It says, I wonder, I see that this experiment can be performed for a cube or for a tetrahedron. But how am I to know that it can be performed for any polyhedron? For instance, are you sure, sir, that any polyhedron,
Difference.
after having a face removed, is it?
Yeah.
Okay, thank you. I need glasses, guys, sorry. Or new glasses. Can be attached flat. Stretched, okay, stretched, thank you. Stretched flat on the blackboard. I am dubious about your first step.
And now it's pupil beta. Are you sure that in triangulating them out, you will always get a new face for any new edge? I am dubious about your second step.
Are you sure that there are only two alternatives? The disappearance of one edge, or else the two edges and a vertex. When one drops the triangles, when one drops the triangles one by one. Are you even sure that one is left with a single triangle at the end of this process? I am dubious about your third step.
Of course I'm not sure.
Gavin.
But then,
We are worse off than before. Instead of one conjecture, we now have at least three. And this you call a proof?
I admit that the traditional name proof for this thought experiment may rightly be considered a bit misleading. I do not think that it establishes the truth of the conjecture.
Oh, what does it do then? What do you think a mathematical proof proves?
This is a subtle question which we shall try to answer later. Till then I propose to retain the time-honoured technical term proof for a thought experiment or quasi-experiment which suggests a decomposition of the original conjecture into sub-conjectures or lemmas, thus embedding it in a possibly quite distant body of knowledge. Our proof, for instance, has embedded the original conjecture about crystals or, say, solids in the theory of rubber sheets. Descartes or Euler the original conjecture conjecture certainly did not even dream of this.
This is good
Section
stuff.
3. Criticism of the proof by counterexamples which are local but not global.
Gosh, still more to read.
Go, yeah.
This decomposition of the conjecture suggested by the proof opens new vistas for testing. The decomposition deploys the conjecture on a wider front, so that our criticism has more targets. We now have at least 3 opportunities for counterexamples instead of 1.
I have already expressed my dislike of your third lemma, viz. That in removing triangles from the network, which resulted from the stretching and subsequent triangulation, we have only 2 possibilities. Either we remove an edge, or we remove 2 edges and a vertex. I suspect that other patterns may emerge when removing a triangle.
Suspicion is not
Full criticism.
certainly. Conjectures ignore dislike and suspicion, but they cannot ignore counterexamples.
Conjectures are obviously very different from those who represent them.
Well, I propose a trivial counterexample. Take the triangular network which results from performing the first 2 operations on a cube.
Back to figure 2.
Now, if I remove a triangle from the inside of this network, as one might take out a piece of a jigsaw puzzle, I remove 1 triangle without removing a single edge or vertex. So, the third lemma is false, and not only in the case of the cube, but for all polyhedra, except the tetrahedron, in the flat network of which all these triangles are boundary triangles. Your proof thus proves the Euler theorem for the tetrahedron. But we already knew that V minus E plus F equals 2 for the tetrahedron, so I prove it!
You are right, but notice that the cube, which is a counterexample to the third lemma, is not also a counterexample to the main conjecture, since for the cube V minus E plus F it does equal 2. You have shown the poverty of the argument, the proof, but not the falsity of our conjecture.
Will you scrap your proof then?
No, criticism is not necessarily destruction. I shall improve my proof so that it will stand up to the criticism.
How?
Before showing how, let me introduce the following terminology. I shall call a local counterexample an example which refutes a lemma without necessarily refuting the main conjecture, and I shall call a global counterexample an example which refutes the main conjecture itself. Thus your counterexample is local but not global. A local but not global counterexample is a criticism of the proof but not of the conjecture.
So, the conjecture may be true, but your proof does not prove it.
True, but I can easily elaborate and improve the proof by replacing the false lemma by a slightly modified one, which your counterexample will not refute. Then that the removal of any triangle follows one of the 2 patterns mentioned, but merely that at each stage of the removal operation, the removal of any boundary triangle follows one of these patterns.
So instead of removing internal triangles, we're only going to remove boundary triangles. That's the idea.
Oh, right. Okay.
All right. Now we're going to
External
skip.
triangles don't count.
Now we're going to skip some stuff and get right to the good part.
Okay.
Is that right? Okay.
Is there going to be a scrap?
Section 4, criticism of the conjecture by global counterexamples. And this is, can I read your part, Kevin?
Yes.
I have a counterexample. Alpha says, I have a counterexample which will falsify your first lemma, but this will also be a counterexample to the main conjecture, i.e. this will be a global counterexample as well.
Indeed, interesting. Let us see.
All right, imagine a solid bounded by a if you will. Okay. Try to draw this is very good, Blackboard.
The cube.
A cube's
I see.
Oh, yeah.
It's within it, so you can't really see it.
Well, yeah,
Right,
you can see it
transparent
if you
cube.
dissected it, but
Yeah,
if
but
you-
it's,
if
yeah.
you buy- yeah.
the inside. The solid itself
Interesting.
is bounded by the because on removing a face from the inner cube, the polyhedron will not be stretchable onto a plane. So I can take a face from in here, that doesn't make it possible to flatten the thing out like it did with the regular cube. Nor will it help to remove a face from the outer cube instead, right? We still can't flatten it out because we have this internal cube that can't be flattened. Okay. Besides, for each of these cubes, v minus e plus f equals 2, right? We already showed that. For the outer cube, v minus e plus f equals 2. For the inner cube, v minus e plus f equals 2. So if you add it all together, you get v minus e plus f equals 4. So the conjecture is false for this example.
Good show. It's good to still say that then. Let us call it counterexample 1.
Surrender.
Sir, your composure baffles me. A single counterexample refutes a conjecture as effectively as 10. The conjecture and its proof have completely misfired. Hands up! You have no surrender. Scrap the false conjecture. Forget about it. Try a radically different new approach.
I agree with you that the conjecture has received a severe criticism by Alpha's counterexample, but it's untrue that the proof has completely misfired, as you say. If, for the time being, you agree to my earlier proposal to use the word proof for a thought experiment, which leads to decomposition of the original conjecture into sub-conjectures, instead of using it in the sense of a guarantee of certain truth, you need not draw this conclusion. My proof certainly proved Euler's conjecture in the first sense, but not necessarily in the second. You are interested only in proofs which, quote, prove what they've set out to prove. I am interested in proofs even if they do not accomplish their intended task. Columbus did not reach India, but he did discover something quite interesting.
Oh, bravo!
Well done, everyone. Well done.
Yeah, that's a new thing.
Yeah, I think there should be more of this.
Can we do some Alan Ayckbourn next time?
That's more like the Goon Show.
That was actually really interesting because one of these last things that Tim's character says is very Popperian, right? He says, your composure baffles me. A single counterexample refutes a conjecture as effectively as 10.
Yeah.
Which is how Popper is usually understood, right?
Yeah.
If our scientific theory predicts that the apparent distance between the star and the sun is x, and we measure it and it turns out to be twice x, then the theory is just wrong and you're done, right?
The theory's got to be checked out, yeah.
But Lakatos sees it differently in this case, at least. He thinks that we can still work with the theory even though it's been refuted.
And that carries over into Lakatos's view in philosophy of science, which was presented as an improvement of on Popper's.
Excellent segue.
Yeah. Methodology, so-called methodology of scientific research programs. Do you want to, should I carry on?
Well, let me just say that probably the two main things that Lakatos is known for are proofs and refutations and the fallibilist conception of mathematics and all that goes with that.
Yeah.
And then on the other side, it's his methodology of scientific research programs.
It is, yeah. So
tell us about that.
Okay. Well, basically, just as you said, Matt, really, it just isn't true if you look at the way that science operates, that if a scientist finds a, quote, refutation of a theory, then they immediately give that theory up. So the classic example, actually, ironically enough, mentioned by Popper, analysed by Popper, but not very adequately, is the discovery of Neptune. So Herschel discovered a new planet, which he named Uranus, just by meticulous observation of the night sky. Planets, by definition, are move relative to the fixed stars.
Wanderers.
But they do so very slowly. So you don't just look in the sky and say, oh, that's a planet. They don't zip along. They go very, very slowly.
No, that's an airplane.
So he discovered it purely observationally in his garden in Slough or wherever it was.
Is it really?
Yeah, but then, Newtonian theorists got to work on what the current Newtonian theory predicted for the orbit of this newly discovered planet, and it turned out that this prediction was completely wrong. Okay, so on Popper's view, at least on the naive version of Popper's view, you say, okay, Newton's theory is out the window, but that's not how Newtonians reacted at all. They said, no, Newton's theory has been right in so many cases. It's much more likely that some auxiliary assumption, as Lakatos would call it, and Duhem had called it before him, is wrong. So basically, in order to get a deduction from about Uranus's orbit, I beg your pardon, from Newtonian theory, you don't just need Newton's theory about gravitation and mechanics itself. You need extra assumptions, particularly an assumption about how many other planets there are in the universe. And obviously, people took it that all the planets there are, all the planets that they then knew about, plus of course this new planet Uranus, but the rest were given. And Adams and Leverrier independently, one in England, one in France, although the French say that it was all Leverrier, said, look, let's assume to the contrary to Popper, if you like, not that they would have known Popper since he was I've got 100 years before you arrived. Let's assume that Newton's theory is correct. What would we have to assume about another planet that we don't yet know about to give us the right results about Uranus from Newton's theory plus the original initial conditions about the planets that they knew about then, plus this extra one? What would we have to assume? And by working backwards, they made a prediction about the existence of another planet called Jupiter.
Wait, Neptune.
Tentatively.
Neptune.
Neptune.
The Jupiter we knew about already.
Sorry, I'm getting. Obviously, that all this working out indicated where Neptune would have to be, what its mass would have to be, and this turned out to be a great success. So by reacting to something that looked like a refutation as something that Kuhn in his famous book The Structure of Scientific Revolutions would refer to as an anomaly, a problem for the theory to solve, there was a great scientific breakthrough, far from being unscientific, as you would gather from regarded as a great scientific success, and surely correctly.
Mm-hmm.
So then the issue is, okay, if you could do that, if you're allowed to say no, it's not the theory that's at fault, it's some other assumption that we don't quite know about, that we must be making, that in order to get this deduction, scientific creationists have long had a problem, obviously, with the fossil record, because the universe was supposed to be created in 4004 BC, roughly speaking, by God, obviously, as it roughly as it now is. But there's all this evidence of stuff that's massively older than that. So it looks like a refutation.
Mm-hmm.
But no, creationist says it's not a refutation at all. Just like in the Newton case, we're going to hold on to our theory and see what else we have to assume, what other auxiliaries. Why should we assume that God created the universe as if it were all new? Why couldn't have God created the universe with some parts of it already looking very, very old? And that obviously stings as science, right? That's the.
But he would do that.
That's pseudoscience, whereas the Newton thing is good science. So I think the main thrust of Lakatos's methodology of scientific research is to explain the difference in you get a new prediction, the existence of Neptune, that you can then test with the Gauss thing, created the universe looking in certain respects. By definition, there's no way of further testing that. So Lakatos would call that the second thing a degenerating problem shift, where there's no you save the theory but purely defensively without any prospect of being tested.
It's got to be able to be held up to examination.
There's got to be some examination to the shift. So
right, not just to the theory,
not
to
the theory,
to the transitions
that,
between
theories. Exactly. So you've got to tell me why we should believe that particular reaction to this anomaly. There are positive scientific reactions where you get independent testability. So you say, okay, the Newton's theory must be right, so I'm going to accommodate Uranus's orbit within it. But you can't just accommodate it by assuming another planet. If you assume another planet, the planet has to be observable. So that's a testable prediction, and turns out to be a correct prediction. But on the Gauss thing, tell me how you could possibly test. You know,
I have an idea. The Gauss dodge seems to imply that God is a deceptive bastard, and therefore we can predict that we'll continue to see God concocting all sorts of deceptions around us, trying to.
Well, that of course is part of the theory that creationists believe. You know, that God makes it difficult to believe. I mean, you know,
don't they tend
you're supposed to go to heaven if you believe, so it can't be easy. So
you don't want to make it too easy.
It makes it tempting to think that there's been evolution, but when there hasn't, by planting this fossil record, you know, so God creates the universe with all these weird fossils already existing in them.
Do they not actually always have a little bit of fallback in, and they can always blame Satan for that? It's going, no, well, God did this, but Satan did all this stuff to like mess everybody up.
Well, but I don't.
Well, then they'd have to imply that Satan created stuff, wouldn't he?
No, he just
came. He just came later and just.
But what's interesting.
I'm not sure Satan's in the picture anymore. So it's even with his grace.
Well, really?
Because you can't believe in an omnipotent being, right? If there's another omnipotent being that alleged, they can't both be omnipotent.
No.
Right? That's
it's almost like religion will eat itself.
I don't want to go too far down this hole, but I think Satan is often thought of as preternatural rather than omnipotent. So Satan and demons can do things that are within the laws of nature, but extremely skillful.
Yeah, but God can't be.
The problem of evil, which you know. No, it's different.
Really?
He can stop Satan from doing things. He just doesn't want to, right?
All right. That's
okay. We just regard Satan as a sort of
another little pawn in God's game.
Yeah. Okay. If it's just the problem of evil, then I agree. You can always do that. Yeah.
Well, that's because it is so full of illogical ideas. But it's interesting in that I'm just thinking about. It just made me think of the whole idea of the appeal of codification of stuff. Really.
What do you mean by codification?
I just mean in the same way as we talked about this, and being able to just to be able to say X equals Y because of Z or whatever, to come up with a rule that kind of covers stuff that you struggle to understand. Understand things better, and I don't know, it just popped up as you were talking about that. This sort of like it's a human, but in terms of this, for example, we're trying to find something that's a definite rule,
right?
That helps us understand and go, that's a face, that's a boundary so far, and that's a hard truth. This is a hard truth. That's good. And by that, and in a way, you kind of make things safe because it's understandable, because things are understandable. And I just, I love it, and I think it's a very, it's a human drive, and that's the same. It's the same drive for religion, really, is because you're trying to make the ununderstandable understandable. Even if you're applying mysticism to it, you're giving rules to that mysticism. And there's ownership to that mysticism that you can then go, okay, I don't have to struggle to understand that anymore. But the pursuit of understanding is an endless quest, and something like this, because I'm new to this, the idea of going, we can refute that proof. No, don't start to think that that's a solid wall. This wall has got some give to it, and actually it might even turn if you push the right panel, and there's a certain, I don't know, it
makes things a little more squishy, right? And I think before sort of the early 60s, when you had Lakatos as well as Kuhn and all these, there was a widespread perception that science and mathematics were very, very reliable and very authoritative, and I think that at that time we came to be faced with these sort of worries that okay, science and mathematics, I think the proofs and refutations is much less well known than say Kuhn, right? But we're faced with these worries that, okay, science doesn't, based on the history that Kuhn gives us, for example, science doesn't seem to be as rational and as solid as we thought it was. And so now we start to worry, how do we know what to believe, right? And there was a great deal of battle within philosophy of science about, is science rational or is it not, which I think was part of Lakatos's well, it's an important part of
Oh,
Lakatos's.
definitely, yeah. That was the whole thing, that he was supposed to reconcile the historical, undeniable insights of Kuhn with a rationalist approach. You know, so his view was that one theory overtakes another, supersedes another, as he would put it, just in case it represents what he called a progressive problem shift. So, you know, not just. So the idea is basically Newton's theory is progressive because for a long time, because when it comes across refutations or anomalies, whatever you want to call them, it deals with them in a progressive way. That is, in a way that yields further predictions that you can test.
So when we see, it's a progressive research program because when we see apparent anomalies, we tend to learn something, new based on the theory rather than upsetting the theory. Yeah, something testable.
Whereas, you know, eventually, so for example, there was this long-standing problem with the details of Mercury's orbit, the so-called precession of Mercury's perihelion, and that was also anomalous for Newton's theory. Scientists postulated another planet, said, oh, let's do the same that we did with Uranus and Neptune, and they postulated there's a new planet called Vulcan that would explain that, but that turned out not to work. It didn't yield. It yielded predictions, but they weren't verified. It wasn't right.
Because they were saying there was
no
planet pulling
its orbit out of what Newton's theory tells us should be.
But we never found the damn planet.
That didn't work. So that eventually Newton's theory itself becomes degenerating. You can only save it by saying, oh, there must be something going on, but we don't know what it is. You know, it's like, you know.
But strictly speaking, for Lakatos,
so that's when Einstein's theory comes along and
supersedes
Newton's, because it's in turn a progressive program.
But hold on for a second. So for Lakatos, strictly speaking, it's not theories that are progressive or not. It's research programs. And what's a research program for Lakatos?
Well, it's really a theoretical system. So he's recognising the fact that you don't test theories in isolation. If you look at the actual structure of a test, just as we saw in that Newton on Uranus case, it's not just that everybody attracts every other in the universe with a force inversely proportional to the square of the distance between them and directly proportional to the product of their mass. Not just that. It's also assumptions about what other objects there are in the universe that are exhibiting a significant gravitational attraction on Uranus. So you have there are also initial conditions or auxiliary assumptions, and so what's being tested is a big theoretical system, and it doesn't just stop at, it's not just the central theory, it's these extra things as well. And there are also ideas, this is where the program comes in, for how to modify it is very much influenced by his work in mathematics, I think, the way that he talks about the positive heuristic of the program. So one part of the positive heuristic in Newton's theory is if you're in trouble, postulate a new planet and see whether that works or not. Mm-hmm. So it's not, you aren't, at least once Adams and Very have done their work, you aren't at a loss. You're looking for some wild conjecture for how current science is turning out not to work. Your current best theory is turning out not to work. You can, that's one thing you can try. I mean, it's not guaranteed to work. Indeed, it didn't work for Mercury's perihelion. But it's a heuristic idea that that's around.
Right.
So there's a programmatic element to science as well. There's a set of ideas on how to develop new auxiliary assumptions.
How to fix things up when you run into trouble.
When you run into trouble that aren't guaranteed to work, but in good science, in the case of good science, do sometimes work, and then you keep a record of how well they're working for individual programs.
And they're progressive if they lead to new discoveries, and they're degenerating if they just lead to more and more epicycles and BS and
so that would be the classic case. So you can reconcile all the data, all the astronomical data, position of the sun, position of the stars, position of the planets, with the fundamental Ptolemaic assumption that the Earth is at rest at the centre of the universe, but only if you give yourself enough epicycles, so planets are not just moving on circles around the Earth, they're moving on circles, and then maybe circles on circles on circles. And you know, you can eventually you can reconcile all the data, but it's at the expense of this great ad hocery, as Lakatos would call it, or a massive amount of.
And it should become clear that
can't be tested. Okay, you're just adding the epicycles to give you what you already know to be the case. That is that Mars looks like it's there at this particular time, on the assumption that the Earth is the centre of things. But in order to do that, you've got to have all these fancy, massively complex assumptions.
And it becomes clear quickly enough that if you add enough epicycles, you can get anything you want.
Yeah.
So you're not really proving anything.
Theorem, right?
Yeah. That's who's
Fourier's theorem. Every period, every closed curve can be an integral of number of circles, isn't it?
Oh, okay.
And that's another mathematical theory.
Yeah. I mean, well, of course they didn't know that at the time, but it's as a matter of fact, that was underwritten by Fourier analysis.
So this methodology that Lakatos has come up with here, that's applicable. I mean, he chose mathematics because it's the crispest, most visual method to explore this idea, or did he was he always just applying it to maths? Is it something that's applicable across the board?
The methodology of scientific research is definitely science rather than maths.
Empirical science.
Empirical science.
Right.
I mean, the way you describe the mathematics, I think, is an indication of another famous criticism of Lakatos, that it only applies to this, that his insights in proofs and refutations only reapply to this almost empirical study. You know, we think of polyhedra as empirical objects, but the set of real numbers is not empirical. Massive, non-measurable infinities are not empirical. They're all very abstract. I mean, most people would not say that mathematics was crisp and
right. Geometry, yes.
But,
sorry,
set theory or algebra, it's fantastically abstract. It's mathematical logic.
Yeah. And so that's and endless as well. I mean, it seems to be through O-level maths, but these ideas, these ideas are interesting. But have you found that you apply this philosophy, because it does seem to be a very distinct philosophy, actually.
No, I mean it's funny because the book really becomes sort of a catalog of methodologies of mathematics, right? They go through many cycles of proofs and refutations and proof adjustments, concept stretching, and what happens in the global conjecture is false. You then go back and sort of tinker with the conjecture a little bit to make it true, and you tinker with the concepts behind the conjecture a little bit. So then the proof works, and then the theorem is true. Right? So we use the proofs not just to establish what's true and what's false, but to help us to sort of carve and shape our own concepts. So as we analyze the proof and see what's working and what doesn't, then we go back and change what the proof was about.
Right. Okay.
So there's a big discussion, for example, what counts as a genuine polyhedron. So, analogously to the ad hoc reaction of creationists to the existence of the fossil record, some people said, for example, this that we drew here with the cube with the cube space in the middle doesn't really count as a polyhedron, right?
That's not what we meant.
That's a monster, as Lakatos somebody calls it. Or they also think about the picture frame, where you've got middle.
Yeah.
It's sort of a polyhedron, but do you want to call it a polyhedron? It turns out that v minus e plus f is not equal to 2 for that either.
And then, of course, you've got the star polyhedra, where you've got the faces sort of slicing through each other and connecting on the other side. That's another sort of monster in Lakatos's conception.
Well, it's he wouldn't. I mean, in the end, he says no. We shouldn't.
We shouldn't call them monsters.
We shouldn't call them monsters, and we shouldn't do a process of monster borrowing. That's like being like Goss, you know, just holding on to the thing. You know, you've got to learn. You've got to get to a more sophisticated conception of what a polyhedron is. But that doesn't mean that you can't have, you know, conditions on it. So in the end, you finish up with for all in this expanded class of polyhedra, if they have this set of characteristics, then v minus e plus f equals 2. If they have these other characteristics, then v minus e plus f is something different. So you get a more general, again, it's like the progressive thing, right? You don't just get
give
defensive.
up.
You don't give up and say, okay, well, I'm just not going to worry about those because they're weird, right? A cube's a nice polyhedron, but I don't want to hear about these sort of things. They're weird. But that's just being, you know, obviously being scientifically defensive and not the right thing to do. So he's trying to tell you how to, what the progressive.
So then
is.
the next step is that you define your polyhedron.
You get a clearer conception. I mean, in the end, it doesn't matter what you call a polyhedron or not. You get a more definite characterization, and you get a much more nuanced. You know, you get something called the Euler characteristic. So different polyhedra have different Euler characteristic. Where the Euler characteristic for a cube is 2, whereas v minus e plus f is 2. But for these other things, then it's a different value. But it's not just plucking those numbers out for particular cases. It's giving you finish up with a systematic account of, you know, why it is for these sorts of objects you get this relationship between, you get differing relationships between the number of vertices, the number of edges, and the number of faces,
and
depending on specifiable characteristics.
And then sort of getting intrigued by the man as well, you know, because you said that he died at 52. Where do you think he was going in his thought? Where do you think he might? Because obviously he's working toward. I mean, this. I think,
or was he finished?
This is No, I mean, how can? I don't know. I don't imagine he could be. You come up with this, which is working towards, you know, a very definite, very honest, and clear way of understanding and defining things, and to be able to accept things, and then also keeping that. I mean, where do you think he might have moved towards? Did he? You know, you said that, you know, he had a big influence on you. Do you feel that there's, you know, there are elements of what he did now that you've taken up and you're still running with?
Yeah. I think he would have moved towards the footnotes. Yeah, it's an interesting question. I mean, he did. I mean, you know, my PhD was basically an application of the principles of the methodology of scientific research programs to not some work in 19th century physics, particularly in optics. You know, the switch from the theory that light consists of tiny material particles fired machine gun fashion, as people like to say, from luminous sources like the sun, to the theory that light consists of vibrations in an all-pervading elastic medium called the luminiferous ether. So, you know, it was massive influence on me. I mean, I was just basically a Lakatosian for a long time. Where he would have gone, I don't know. As I say, I think.
I mean, it is like asking, you know, where's the rainbow end, I suppose. But
he did have a fascinating life. We could talk about his life if you want.
Yeah, actually. So why was it called Imre Lakatos?
Well, he was Hungarian, obviously. Got his first PhD in Debrecen in Hungary. He got caught up in the Second World War, as you might expect. So when I think it was only 1944 that the Germans invaded Hungary, he was then on the run because he was Jewish from the Gestapo.
His surname was originally.
His surname was originally Lipschitz, Imre Lipschitz. His father emigrated to Australia before the Second World War started.
Was a guy in analysis called Lipschitz. No relation.
Yeah, I don't. There's lots of people called Lipschitz.
Lots of you.
It's not. It's a very common name, I think. Yeah. So he was. And there's a famous story we could go into or not about.
we like a tangent.
He was leading this he was the sort of unofficial leader of a group of young Jews who were living on false papers, trying to keep out of the way of the Gestapo. And there was one particular member, a young woman called Ava. They were all called Ava. All Imre's women, nearly all. He had lots of women. Who had particularly, who seems to have been a bit depressive maybe, I don't know, it depends who you talk to. Certainly had weaker papers, and they had a group discussion and decided that she ought to commit suicide because if she was by the Gestapo, she would almost certainly confess and give all the information to these other people.
It's a hard test of logic.
It is, and he was vilified later by in a book that was much read in intellectual Budapest by her sister, obviously in the 70s or 80s. I've never known what to think about that. I mean, you know, it's well known that American servicemen parachuting into occupied territory, German occupied territory, carried cyanide in case they were caught. To survive the Second War, his mother and grandmother were both perished in Auschwitz. He then became after the war became quite a high, more sort of deputy minister of education in sort of Stalinist Hungary, communist Hungary, but then got into trouble largely again over women, I think. But there was some guy who was higher up than him who got him into trouble, and this Ava Rosette's thing came up, and he was held in solitary confinement for a long time in Rex, the worst of all the Hungarian gulags, and only got out just before the Hungarian Revolution in 1956. So he had an incredibly colourful life. He was really
but also a life made with a lot of life and death decisions, and
exactly.
very difficult decisions, and to make. I don't know, just obviously I'm always fascinated by human nature, but it's almost like, do you, when you've been through processes like that and you've had to make decisions and act in certain ways, it shapes the way one you think, but also how difficult it is to think about things, because you've had to think about really important life and death decisions and things like that. So you can apply that mental energy to working on something like this. But I'm just wondering, you know, I'm just also always interested about the influences and what shapes people, what makes them the thinkers they are, really.
No, it's true.
And I don't know. I mean, it sounds like a fascinating man. You know, it's totally new to me.
Do you think that his experience in the war and politics and influence on the philosophy he eventually produced in any way? I mean, it's hard to see a connection.
Yeah, I don't know.
I mean, a mind is a mind.
I mean, he was fearless. I mean, you know,
he was quite a radical.
Quite a radical. I think that, you know, and certainly the way that he, you know, operated with LSE politics. You know, it was all pathetic for him because, you know, a little bit, you know, academic squabbling. So when he'd been, deciding whether people should commit suicide or not, whether, how to survive, you know, solitary confinement for years. And
I mean, challenging authority was certainly second nature. If he, you know,
exactly. And
challenging accepted thought.
Yeah.
Standing up for things.
Yeah, exactly. I think that. So, but. I mean, you know, he got it in between this. Before he became Minister of Deputy Minister of Education, he was employed at the Hungarian Academy of Sciences, and that's where he was translating in Anglo-American books into English, and that's where he came across Popper. That's where, apparently, Popper has a famous book called The Open Society and Its Enemies, which is more in political philosophy than in scientific philosophy, which is where he really made his name. But it probably more influential than anything he wrote in philosophy.
And they were contemporaries.
Well, Imre was 30, 40 years younger than Popper.
Right.
But he finished up. Popper was at the LSE. He appointed Lakatos to the LSE, and they had a fiery relationship, as you might expect. Which is also talk about.
And also his name, were you saying that it meant locksmith?
Yeah, so sorry, I didn't get to the name. Yeah, so he changed his name when he was on the run from the Nazis. He changed his name to Imre Molnar, which apparently is a nice, non-Jewish, middle-class American, Hungarian name. But then, after the war, so they must have been quite rich, I think. But the story is that he got back to Debrecen, where he lived, and there were lots and lots of monogrammed shirts that he owned. He was quite a vain, sort of dapper man, actually. With IL, so he had to think, oh, I can't be Imre Molnar anymore. So, and how should I change my name? Well, it should be something nice and working class, given that we're now in the Soviet era. Yeah. So he changed it to Imre Lakatos, or Lakatos Imre. Because I say that means locksmith, so it sounded nice and working class.
You know about him before you met him?
Oh, of course not.
No, you
didn't.
I was a
working class lad. I was just at the LSE because I had a 10-minute discussion on careers, and we decided I'd be hopeless in business. I wanted to be rich. So the best thing to be would be an actuary. This is more or less this way I went, because that was the highest paid profession on average, and I had no idea what actuaries did. So where should I go to study to be an actuary? LSE to do stats. So I went to LSE, was a statistician for the first year, and just sat in on Popper's lectures, which Imre used to attend, and was fascinated and switched to philosophy. So I was introduced to Lakatos then as my undergraduate tutor, amazingly enough. And he said, I don't want to talk to you again until you've read the following books. And he gave me this great long list of books. Courant and Robbins, What is Mathematics, I remember. Stoll, Set Theory and Logic. Who were those people who did the Holton and Roller, the metaphysical foundations of modern physical science, something like that. Anyway, there was a whole list of it. And to do all the exercises. Sorry? Yeah, polio, how to solve it. Yeah.
How to solve it.
Yeah.
Okay. Which was polio, how to solve it is reportedly a big influence on.
Well, it is. You can see it.
Yeah. If you've read polio, I haven't. So.
No, it's. Anyway, yeah. So he said, and I think the expectation was he didn't like to work with students if he could avoid it.
So give them a bunch of books, tell them not to come back.
Not to come back until you've done this, and believe that they couldn't. And I was in tears some of the time, because it's not easy to learn mathematical logic on your own, especially when this book was full of misprints.
Oh no!
The answers at the back were wrong, and I thought, I'm sure I got that.
Oh, that's maddening.
Anyway, I went back to him at Christmas, and he was obviously surprised, and all the exercises worked out.
Fixed the errors.
He said, I think you are what did he call it? A hopeful monster. It was a term that was prevalent then in evolutionary biology, meaning a mutation that looks initially like it is destined for extinction, but might actually just about get through, because it's sort of different.
Might carry some fitness.
Might carry some fitness value that we can't quite see yet. I think you are a hopeful monster.
A hopeful monster.
So he was. From then on, he was. And he took over your life. If once you were on the inner circle, then it was constantly going out to his place in Hampstead and talking about philosophy. He was just 24/7 philosopher.
Yeah, lived it, breathed it.
Everything. And terrible political views, but that's another.
Well, we should dwell on the hopeful monsters. Hopeful, because I think that's what that's the secret to moving on.
Well, John, we have a little tradition here, which is that once the bottle of wine is empty and the glasses are empty,
We
the
smashed
show
it
is
over.
over.
We smash it, and the show is over.
Okay.
But
Well, it was fun.
I really thank you for coming here to talk about Lakatos,
fabulous.
one of my big philosophical heroes, and I hope that we can have you back again to talk more about your own work.
Oh, okay, we could do that. Yeah.
Randomized clinical trials
All that stuff,
and structural realism.
Yeah.
But in the meantime,
Where's your heart, man? It's there.
now we'll play the theme again, and we'll play a bit longer and have a little fun with it.
And but still on one chord.
Still on one chord.
Oh, yes.
Oh, so
John-
an extra one in if you want.
John is from the old school. where
Three
you
chords
need
is
three chords.
maximum. I'm used to three. You know.
Maximum and minimum. Where's my harmonica actually?
Is it here?
That looks like a harmonica.
Does it sound like a harmonica?
It's still a harmonica.
Oh, but except this one's backwards. The low notes are on the right instead of on the left.
Oh no.
It's a big problem. All right.